Hi everyone. Astronomy for A level starts with a definition for standard candles that is used as an astronomical uh, object, as a reference object exactly, with a specific luminosity. And relating this luminosity, this could serve us to find the distance to Earth. Standard candles are classified in two types. The first type, so let's first specify the definition of a standard candle. So standard candle is an astronomical object of known luminosity so that this can serve, as I said, in measuring the distance separating a star in a very far galaxy from Earth, rather than using the parallax that has many limitation in measuring uh, galaxies and uh, bright objects at the distances farther than 100 light years. So the standard candles and its two types enabled us since the beginning of the last century to measure farther distances for galaxies. The first type of standard candle is the Cepheid variable. A Cepheid variable is a star that is going brighter and dimmer in a periodic manner. This period was actually related to the luminosity of this star, and it is found uh, at the beginning of the last century that this is the scientist Henrik Leavitt found that a Cepheid variable is a star that is having its brightness changing in a periodic manner. Here it goes to a maximum brightness. Here it becomes dimmer and dimmer until it reaches minimum brightness. And the brightness will grow up again. And this will be considered a full cycle of this Cepheid variable. In this example that is shown here, the period extends from day 3 to around day 9. Therefore, in a period of about 6 days. Henrietta Leavitt relates the length of the period to the luminosity of stars. In this graph, it is shown that the more is the period, the more is the luminosity of a star. And clearly by drawing a best fit line here, we can see a strong positive relationship between uh, luminosity and the period. Luminosity is hard to be measured uh, for a star specifically, but it is related to a known luminosity, related to a specific luminosity. And here we are relating all the luminosities of all stars to the luminosity of Sun, as we see here. So for example, if a star is getting a luminosity of 10, this means that it is 10 times as luminous as Sun. That has a known luminosity of about 3.83 times 10 to the power of 26 watt. And this will be represented throughout our work as L0, will be luminosity of Sun, which is around 3.8 or 3.83 times 10 to the power of 26 watt. Another type of standard candle is the type 1A supernova. 1A supernova is a white dwarf that absorbs energy and therefore it gains mass until it reaches a limit where it explodes emitting radiations. The received radiations, and by using the same way, the same principle that we used in Cepheid variable, radiations emitted by this supernova will also enable us to determine how far it is from Earth. So we could specify here, be more specific when talking about Cepheid variable, that Cepheid variables are pulsating stars that cyclically or periodically grow brighter and dimmer. All right. And that there is a direct correlation between the pulsation period and luminosities. The type 1A supernova is nothing here to highlight, just we need to remember that it absorbs energy or mass from a neighboring star. At the beginning, it is a white dwarf, and then it explodes, emitting radiations that enables the measuring of distance. The table shown here, you see it relates the luminosity of different stars to that of Sun that is taken as a reference. You see here that luminosity of Sun is taken as 1. So when I say, for example, a star like Vega has a luminosity of 40, this means it is 40 as luminous as Sun. So they are all related to Sun. Now, knowing the luminosity of a star, knowing also its radiant flux intensity or brightness, F, and therefore we could find how far it is from Earth using the inverse square law. By the way, 4 pi r square or 4 pi d square is the area of a sphere. This shows that radiations are emitted in a spherical wave, where at the center of this sphere we have the star, and it will be required to find the distance, that is how far this star from an observation center, usually Earth. So as I said, area of sphere is taken as 4 pi r or d squared here. Applying this inverse square law in the following example, where I have a star of luminosity given by 3.8 times 10 to the power of 31 watt power, and placed 1.8 times 10 to the power of 24 meters away from Earth. So in a direct application for the law F, the radiant flux intensity is given by L over 4 pi d squared. Plugging the numbers, we have 1 or 3.8 times 10 exponent 31 divided by 4 pi, and 1.8 times 10 exponent 24, and then squaring it to get the answer. So I have 3.8 10 exponent 31 divided by 4 pi, 1.8 10 to the power of 24, and then squaring, and the answer is 9.3 times 10 to the exponent negative 19 watt per meter squared. Another example here, I think this paper is a February-March paper, maybe year 22. In this question, the state in part A, state what is meant by luminosity of a star. Luminosity of a star is the power or the total power of radiation emitted by a star. So it is the total power we have to fix the color. Let's do it again. by a star. Okay. Then it says that luminosity of sun is this much, as we know it, standard luminosity or standard power, radiation power. And the distance to Earth is given. And they want me to find F. In this case, with this distance, F is equal to L over 4 pi d squared. So this is taken as d, this is L. Placing the given numbers, 3.83 times 10 to the power of 26 divided by 4 pi times 1.51 times 10 to the power 11. Calculating the values here, so I have 3.83 again, 10 to the power of 26 divided by 4 times pi times 1.51, 10 to the power of 11 and squared, and the answer is around 1,340 thousand 340. The unit is watt per meter squared. Says next, use the data from B to calculate the mass that is converted into energy every second. The power is given as 3.83 times 10 to the power of 26, which means that energy per second is the same as that number. So E is equal to 3.83 times 10 to the power of 26, but it is joules now. And from E equals mc squared, m that is converted to energy is going to be E over c squared, which is the speed of electromagnetic radiations propagating in space, power 26 divided by 3 times 10 to the power of 8, and then all squared. All right, so yeah, and 3.38 10 to the power over 26 divided by 3 10 to the power of 8, squaring then, and the answer is around, sorry, 3.83. Let's fix this. 3.83 divided by 3 times 10 to the power of 8, all squared. And the answer is around 4.26 times 10 to the power of 9. So 4.26 times 10 to the power of 9. and this is kilograms. So this is the amount of mass that is converted to energy every second.